We've been talking about chapter 12, which is bonding. And again, last time we talked about several different types of bonding. We have, again, our ionic bonding, which is our metal and non-metal together. And again, because of those periodic trends, what we definitely see happen with this situation is we do see a transfer of electrons from our metal to our non-metal. Because again, our metals have pretty much all those properties as we talked about there sort of briefly before we get to chapter 11, to want to sort of release their electrons. They want to give away their electrons. They really don't want to hang on to their electrons. So it doesn't take a lot of convincing for them to lose them. And that's very different properties than what happens with nonmetals. Nonmetals pretty much have the complete opposite sort of properties. They're all about hanging on to their electrons, bringing more electrons towards themselves. So when these two guys get together, it results in a transfer of electrons, and that results in ions being formed. So that results in, again, our metal becoming a cation, our non-metal becoming an anion. And once again here, the importance of an ionic bond is there's no sharing of electrons. It's that positive opposite attraction there that holds that together, that electrostatic attraction. And then on the other hand, we do have covalent bonding, which is between two nonmetals. And because they are, again, nonmetals that are involved here, they are obviously in the same sort of spot there on the periodic table and pretty much the same location. So they both share the same sort of properties as all nonmetals, which is they want to really hang on to their electrons. They want to bring electrons towards themselves. So unlike an ionic bond where we do get that transfer of electrons, because in a covalent bond, they both really want to hold on to the electrons. They end up basically sharing electrons. So we get the sharing of electrons that basically happen here. And that sharing of electrons can be equal sharing, and an equal sharing of electrons is what's known as a nonpolar bond. They can be unequal sharing of electrons, and that is what is referred to as a polar covalent bond. And you could kind of think of those type of bonds as being sort of nonpolar as sort of like a neutral bond, because there's sort of equal sharing of electrons. There's really no side to that bond that's more positive or negative. You know, there's sort of an even distribution of that negative electron charge along with the positive charge from the nucleus. And that's different than what happens in a polar bond. A polar bond usually results from basically a significant sort of difference in electronegativity of the two atoms that are involved in that bond. And the one being more electronegative is the one that's going to bring the electrons towards itself. The result of that is it will become partially negative, the side that's more electronegative, and it will become partially positive, the side that's less electronegative. So a couple of those examples that we looked at was something like HF. Again, F being the most electronegative atom you could have, means that the electrons are really hanging out towards the fluorine side is going to be more negative, and the hydrogen side here will be more positive. We could draw that arrow, which always points to the more electronegative atom. And again, the back part of the arrow, which kind of makes like a plus sign, always is pointing towards the positive side of the bond. And that is what is sometimes referred to as a bond dipole arrow. And that is used to indicate a polar bond. We don't use that arrow in a nonpolar bond, again, because there is no positive or negative side. So something like F2 would be nonpolar. We would expect the, again, electrons to be shared equally. And again, with our HF, that creates that partially negative charge and partially positive charge that happens there on the hydrogen. As we also talked about, they are partially positive, partially negative, because there is still some aspect of sharing that's happening with those. So there hasn't been a complete transfer of electrons like we see in an ionic bond, where we get a full sort of negative charge and a full positive charge that basically occurs. We also looked at electronegativity and really the difference in electronegativity to help us decide, you know, what type of bond we would have, what type of sharing that we would have. So if we have a difference in electronegativity between, say, 0 to 0.4, that is considered a nonpolar bond. And this would be using the electronegativity values from Pauling that go from 0 to 4, 4 being the most electronegative. Anywhere above that, so you could call it 0.5 to less than 2, is some type of polar bond. And again, an ionic bond is typically above 2. Remember, though, that as we talked about, you really don't need the difference in electronegativity values really to determine ionic bond. As soon as you see a metal and a non-metal, you know it's ionic, so you don't really need it. We also talked about that you can use the general trends in electronegativity to make a pretty good assumption about polarity, especially if you're comparing two things that are in the same row. And if somebody's in the same row or period on the periodic table, the guy further to the right should be more electronegative, and that should result in a polar bond. Also, if you're comparing two things that are in the same group, the one that's further up in the group should be more electronegative, and that usually will result in a polar bond. So there's a lot of instances you may not need the actual numbers. You can make a pretty good sort of guess as to polarity based on the position on the periodic table. Remember as well that there is sort of a diagonal relationship between certain elements where they will have the same electronegativity values. So like carbon, I'll say it right, carbon and sulfur, they are diagonal of each other on the periodic table. They actually share the same electronegativity value as carbon is further up, but sulfur is further to the right, so they sort of cancel their differences. You also see that with like nitrogen and chlorine as well, that sort of diagonal relationship where they are. So it is possible to get two different elements that actually will share the same electronegativity values and actually be a nonpolar bond, especially if they're sort of diagonal of each other. Not directly diagonal, but kind of diagonal and over one, if you will, on the periodic table. Any questions on any of that stuff we did last time, I think? Yeah. Okay. So as we saw, atoms with widely different electronegativities, again, tend to form ionic bonds. And that's really, again, because we got these guys with very different sort of needs in terms of electrons and what they want to do with those. And obviously, when we get into that non-metal region, we're going to get those covalent bonds that are going to form. And that's why we generally see metal, non-metal ionic, and covalent bond, basically two nonmetals together. So here is again sort of that breakdown, and as we talked about, and as we also saw, I think when we were looking at the electronegativity values, again, there is a lot of combinations of metals and nonmetals that will give you a value less than 2 when you take the difference in electronegativity, but they're still ionic. So that kind of 2 cutoff for ionic is just sort of, in most cases, rather than a really hard cutoff for everybody. Now, sometimes people refer to sort of bonding in terms of percent ionic character, and percent ionic character means that if you have 100% ionic character, that's going to be an ionic bond. And if you have 0% ionic character, then you have a nonpolar bond, and then obviously between would be somewhere that is polar. So not too often, but people sometimes refer to bond polarity in terms of percent ionic character, and it's sort of just a different sort of scale to basically talk about what we were doing before. This would be obviously 100% ionic on this end. It's basically 0% on that end where we have equal sharing, and sort of percentage in between there on our polar guy. All right, so about ionic. Really, the steps that you should follow to draw Lewis structures for covalent bonding or molecular compounds where we're sharing electrons. So these are really the steps that we want to follow when we're drawing for covalent bonding. And when you do draw your Lewis structures, I would highly recommend that you follow these steps, because it should lead you to a proper picture when it's all said and done. You do not want to do drawing Lewis structures by, I guess, like it's sometimes referred to it as like piecework, where you just draw all the individual sort of Lewis dot symbols for all the symbols and try to figure out how they all come together. And usually what happens in that case, if you sort of do it in piecework, you'll end up with too many electrons, not the right number of bonds and stuff like this. Now, if you follow these steps, again, it should lead you to a pretty good structure at the end. And when we think about electrons, we want to think about them as being able to be sort of distributed equally, if you will, amongst all the elements that are involved. We don't want to think about, well, nitrogen has 5, so he's got 5 and needs 3 more, or whatever it may be. So we want to think about just the total number of electrons and sort of distribute them equally, and you'll get sort of a good picture. The first thing you want to think about is the logical sort of arrangement of your molecule that you're drawing. There is sort of some rules to help you decide what should be in the middle. So typically in the center position is the least electronegative atom. So the one that is the least electronegative is usually the guy in the middle. I will say a lot of things that we draw in this class, and most of the time you draw, it will have one central atom, but there is possibility you could have multiple sort of central atoms in a picture. But in a lot of times what we'll come across usually is like one guy in the middle and like everybody's attached to it. But you can definitely have places where you have multiple central atoms. Because the least electronegative needs to be in the center, that means that hydrogen should never be there. That's also because hydrogen should only have 2 electrons, right? So again, if you put hydrogen in the middle, it's going to have way more than 2 electrons, and obviously that can't happen. And then obviously fluorine should not be in the middle either, because it is the most electronegative atom that you could have along the way. Count the total number of valence electrons is probably the most important thing. When you count up the total number of valence electrons, that needs to be in the entire molecule that you're drawing, or ion that you may be drawing. Now, if you are drawing something that's a polyatomic ion, which is nonmetals together covalently bonded and sharing of electrons but have an overall charge, you need to also take into account the charge. So something with a negative charge means that it has gained electrons, and something with a positive charge means that it has lost electrons. So you do need to subtract that charge off. So you do need to take that into account when you are adding them up. Otherwise, you will be short in terms of your electrons. The next thing that you want to do is, now that you have the logical arrangement and you know the total number of valence electrons that you should have in your picture, and again, that total number is important because you got to have exactly that number when you are done drawing. You want to make one single bond from the center to each of the outside bonds. And at that point, you will still have some electrons left over. Those electrons then are put on the outside atoms first in pairs, so dots, until each of the outside atoms has 8 electrons, or if it's hydrogen, obviously no dots, so it'll be done. Once you've done that and you filled up all the outside atoms first with dots and of electrons, then you go to the center atom and you put those electrons on dots if you still have more. At that point, once you reach the center atom, you should have no more dots. You should be out of electrons. The last thing that you want to make sure of is that you have met the octet rule. It's really at that point, if somebody has not met the octet rule, that is where you want to try to fix it. And the way that we try to fix it is to make a double bond first, try to exhaust all the double bonds that you can do. And then if that still doesn't fix it, then you want to go to a triple bond situation after that. So you definitely do not want a double bond or triple bond right out of the box, which is what very commonly people want to do because it makes it look more chemistry-like or something like that. But you do want to kind of save double bonds and triple bonds to fix a situation where you do not meet the octet rule. All right, so let's do one here together to see how we go through all these steps. So we're going to draw NF3. So the first thing that we want to do is figure out the total number of valence electrons. So nitrogen is 5. And again, remember that it equals the group number from the periodic table. So that's our nitrogen. We have 3 fluorines, each is group 7, which means it has 7 valence electrons. That's 21 and 26 valence electrons. So that number is really important because, again, our picture needs to have exactly 26 when it's all said and done. Now, clearly, between nitrogen and fluorine, nitrogen is the least electronegative atom, so that should be in the center, and fluorine should be on the outside. And just by common sense as well, a lot of times when you have one element and like multiples of the other, usually the one element's in the center and the other ones are attached in most cases, is how it sort of works out. So logically, this is going to be arranged like this, as again, nitrogen being our least electronegative atom. That third fluorine there could be put up on top or bottom. It doesn't really matter where you put it. The first thing I want to do is make one single bond from the center to each of the outside atoms. And I'm going to use, again, lines to represent my bonding electrons here. Remember that each line represents 2 electrons. So that's a grand total of 2, 4, and 6 electrons I have used at this point. And if we just do a quick subtraction, that means I got about 20 more electrons that I have to put on this picture. So those 20 electrons, we're going to start on the outside and then work our way in. And they're going to be put on as dots and pairs of dots. So that's going to be 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have put on my picture a grand total of 24 electrons. I still actually have 2 more to go. And now that I filled up all the outside ones with 8, we're going to go to the center atom and put those on as dots as well. And now I have placed on there all 26 of my electrons. The last thing that I want to do is make sure that everybody has met the octet rule. And that means, again, everybody should have 8 electrons except for hydrogen if it happens to be there. So if we look at the fluorine, that is 2, 4, 6, and 8. All the fluorines are exactly the same. So 2, 4, 6, and 8. 2, 4, 6, and 8. And when we look at our nitrogen, 2, 4, 6, and 8. So everybody has met the octet rule. And that would be the proper picture before I graffitied it with all the highlighting, but it would be that before the highlighting part. Any questions on those steps? So basically single bond, pairs of electron on the outside to get everybody to 8, and then work your way to the center atom if necessary to put dots, and then make sure everybody's met the octet rule. So since everybody's met the octet rule here, there's no need to double bond or triple bond, again, to make it fancier or wrong or anything like that. Any questions? All right, so why don't you try the next one I think you might have, which should be maybe this. Why don't you try NO3 minus? Might be a little different than what's on your notes. So why don't you give that one a go? We got nitrogen, which is 5. I'll get something right with, actually, might be better. All right, so nitrogen is 5. We do have 3 oxygens, which each is group 6. And we do have a negative charge here, which means it did gain an electron. So we do have to add 1 more to our total here for that negative charge. That's going to be 18, 19, 24 valence electrons. Once again, in this case, if we look at the periodic table, we see nitrogen, oxygen, fluorine. So going this way, oxygen is more electronegative. So that means nitrogen is least electronegative. So it should be in the center. And again, there's only 1 nitrogen in this case, so it probably should be in the center. So we're going to do our nitrogen in the center. We're going to put our oxygens around. And once again, here, we're just going to simply do a single bond to each of the outside atoms. That's going to give me 2, 4, and 6 electrons. That's going to leave me 18 more to go. Once again, they're going to go as pairs on the outside until they have 8. So that's 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have now placed 24 electrons on my picture. Is everybody good in this case? They are not. Nitrogen is actually short, right? So all the oxygens are good. The oxygen's got 2, 4, 6, and 8 electrons. But when we look at the nitrogen, it has 2, 4, and 6 electrons. So it's actually short. So this is a situation where we have obviously applied all of our electrons, and we are short of the octet rule. So in this case, we do need to fix that. So can I fix it by just laying in a couple of dots there? I cannot, because now I have 26 electrons, which is too many, right? So again, that 24 number is really important, so you can't do that. So this is a situation where we do need to make a double bond to try to fix it. And in this case, all the oxygens are pretty much the same. So you could double bond it up at either of the oxygens or any of those oxygens there. So can I just put a line like so? I cannot just do that because same reason, I now have 26 electrons. Oxygen's got way too many electrons at that point as well. So when we go to make a double bond, we actually are going to take a pair of electrons and we're going to move them in. So I'm going to take a pair of electrons and basically move them in to make that double bond. The result of that is we will end up with something that looks like this. And usually we'll put a little bracket around it with the charge on the outside, since it is an ion and it does have a charge. Now, when we look at it, the oxygens are good, both the top and the bottom there. We got 1, 2, 4, 6, 8 electrons. We got 2, 4, 6, 8 electrons for that oxygen. And for the nitrogen, we have 2, 4, 6, 8 electrons for the nitrogens. So everybody has 8 electrons. We still only have a grand total of 24 electrons, which is what we're looking for in this particular case. Questions on that there? Now, we could have double bonded to either of the other oxygens as well. So we could have just as easily drew a Lewis structure where we double bonded there to the left by bringing those electrons in. And we could have double bonded there to the right by bringing those electrons in on the right. And all these structures are what are referred to as being resonance structures of each other. And resonance structures arise in a situation like this where there's more than one option as to where you can make that double bond. And pretty much the true structure is somewhere in between, though, because those double bond electrons are what are referred to as being delocalized, which means at any given time, they may be over here at this oxygen, but then they may be up there at that oxygen. They may be over there at that oxygen on the right. So they're kind of moving around. So the true structure is probably somewhere between all three of these, and they're all equivalent sort of structures. So you don't necessarily have to draw the resonance structure all the time when it occurs, but obviously if it asks you to do so, you should. And it's basically simply just moving the double bond to all the possible locations where you can make a double bond. If you were just asked to draw a Lewis structure for this compound, any one of the three structures would be fine. If you just wanted to draw any one of those three. Any questions on double bonds here? Okay. All right, so let's do a few more here just to make sure. Let's do H2S. Let's do NH4 plus. Let's do CH2O. Let's do SO2. And let's do a little N2. All right, draw proper Lewis structures for each of these. Okay, let's take a look, see how you're doing on these. So again, we want to follow our sort of rules. So we'll start with the top guy there, which is H2S. So we're going to count up our total number of valence electrons. So 2 times 1 for the hydrogens and 6 there for our sulfur. That is 8 valence electrons. Obviously, hydrogen cannot be in the middle, so that's going to leave sulfur in the middle. Hydrogen will be on the either side. Once again, we're going to connect with a single bond. That's going to give us 2 and 4 electrons. We have 4 more to go. Am I putting dots on hydrogen? I am not, because I don't want an X, right? So they are full with 2. So now we will go to our central atom here and we will put our dots. And now we have our 8 valence electrons that are on there. And again, sulfur's got 8, and both of the hydrogens have only 2, which is what it should have. And that would be our correct structure there. Question on that one. Taking a look at NH4 plus. Once again, we have nitrogen, which is 5, 4 hydrogens, each at 1. And now with a positive charge, that means that it has lost an electron. So we need to subtract that off from our total here. So we'll go with -1 because of that. And that's going to give us 9 minus 1, which is 8 valence electrons. Once again here, nitrogen has to go in the middle because hydrogen cannot. So we'll do our hydrogens around. We'll do a single bond from the center to the outside. That is 2, 4, 6, 8. Who do we appreciate? That is it there. Yeah, that is 8 electrons. Our nitrogen has 8 electrons around it, and each of the hydrogens have 2. And again, we put some brackets around it with a positive charge because it is an ion in this case. Any questions on that one there? Looking at the next one here, we got CH2. Oh, carbon is 4. There are 2 hydrogens each at 1, and our oxygen at 6 in terms of our electrons. That is 12 electrons in this case. We know for sure that hydrogen should not be in the middle. And when we compare carbon and oxygen, which one is more electronegative? It is oxygen. They're in the same row on the periodic table, and oxygen is further to the right. So again, when we look at the periodic table, we have that situation. So we know oxygen is more electronegative. So it actually should be carbon in the middle. And we got our hydrogens and our oxygen in this case. So we're going to do the same thing, single bond. That gives me 2, 4, 6 electrons, leaves me 6 more to go. We won't put any on the hydrogens on the outside, but we can put it on the oxygen on the outside. So we'll put those there. That's going to give me 2, 4, and 6. At this point, I have all 12 electrons. Is everybody good in this case? They are not. It is carbon that is short, right? So carbon here has only 6. The oxygen's good. The hydrogens are good. So in this case, this is where we want to make a double bond to try to fix it. Once again, we're going to take a pair of electrons and bring it in to do so. And that will then give us a double bond action happening. Looks something like this. And now that oxygen up on top that's double bonded has 8 electrons. And now our carbon has 2, 4, 6, and 8 electrons. So it is good as well. Any questions on that one there? Okay, next one is SO2. SO2 is 6 for the sulfur, 2 times 6 for the oxygen. That's a lot of math there. 18 we'll go with. Once again, if we look at sulfur and oxygen on the periodic table, we have something like this, which means oxygen is more electronegative as it goes up in the group. And that means sulfur should be in the middle. Oxygen should be on the sides. And we're going to do a single bond to each. That is going to be 2, 4 electrons. I have 14 more to go. So that's going to be 2, 4, 6, 8, 10, 12. At this point, I have put on 16 electrons, still have 2 more to go. They go on the center as dots. That's how they get there, by the way, not double bonded up because it looks that way on Google. Yeah, so it actually should have those dots right there. At this point, is everybody good at this point? Our sulfur here is going to be short in terms of electrons. It's got only 6. So here we can make a double bond to try to fix it. And doesn't matter which side I make a double bond from. It doesn't. They're both the same. They're both equivalent oxygen. So I could take a pair of electrons and bring it in. And that would give me a double bonded oxygen on the right. This is one that we could also draw a resonance structure for, where we could have double bonded the oxygen on the left. It'll look something like that. So again, either one of those structures would have been fine, and they are resonance structures of each other. Any questions on that there? Lastly, then, we have our nitrogen, which is 2 times 5, which is 10 valence electrons. There is really no central atom here, so we're just going to line them up next to each other. And we could do the same thing as we've done before. We're just going to connect them with a single bond, which means that's 2 electrons. We still have 8 more to go. We'll put it on the outside. So 2, 4, 6, and 8. In this case, the nitrogen on the left is quite short. Yeah, it's only got 4 electrons. So we'll try to fix it by making a double bond. So we're going to bring it in to do so. And if we do that, we will end up with a double bond that looks something like this. Nitrogen on the left is affixed. No, it got better. It's now at 6, right? So this is a case where there is no more chance to make a double bond. So now we want to go and make a triple bond. Works the same way. We're going to take another pair of electrons and bring them in to make the triple bond. So we'll take a pair of electrons and bring them in one more time. And that is how nitrogen ends up with a triple bond on it. And now both nitrogens have 8, and they're happy in that sense. So making a triple bond works the same way as making a double bond. You again just bring another pair of electrons in. As I mentioned before, if there is an opportunity to maybe double bond before you triple bond, that's sort of the order you want to do it. Single bond, then if it's not fixed, double bond, do all the possible double bonds you can. Then if not fixed, go to triple bond. And that usually, again, will give you pretty good structure when it's all said and done. Any questions on any of these or how to draw these Lewis structures here? So if we look at one more here, which is sort of a offshoot of one of the ones we did, we look at something, for example, like nitric acid, which actually has multiple central atoms. We have 1 for the hydrogen, we have 5 for the nitrogen, and 3 times 6, which is 18, 19, 24 valence electrons. Because this actually is an acid, it has a little different sort of connectivity. We still have our nitrogen in the middle, but we actually have a hydrogen that's attached to the oxygen. That's actually what makes it an acid. So if it's a situation like this where you might not know how it's connected, I would obviously give you some information as to how it's all connected. But in this case, you can see we actually have 2 central atoms, the nitrogen and the oxygen. And we would still follow the same procedure as we did before. We're just going to connect everybody up here with single bonds. So we're going to do a single bond action to everybody. That's going to give me 2, 4, 6, 8 electrons. That means that we have 16 more to go. We're going to work again outside in. So hydrogen will not get anything because it's done. So the oxygen on the outside here will get some electrons. So 2, 4, 6, 8, 10, 12. At this point, I have put on there 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. I actually still have 4 more to go. The next sort of outside atom is the oxygen on the right. Yeah, so again, kind of working outside in. So we'll go to the oxygen on the right, which can hold some electrons. And there are our electrons. That is now 24 electrons in this case. Is everybody good in this case? The one element that is not good is which one? Nitrogen. It has only 6. So we still will do our same process. We can make a double bond. In this case, you most likely will probably either double bond here or here. This is actually what makes it an acid, so you probably wouldn't lay up a double bond towards that end on that oxygen, but so you wouldn't probably go there. So I'm going to double bond here by bringing it in, and we will end up with a structure that looks like this. You could also draw a resonance structure for this guy where you double bonded there to the left as well. So even with multiple central atoms, you could still follow the same sort of steps, and it should get you to a pretty good structure. Any questions on that there? All right, and obviously this is covalent bonding, sharing of electrons, so that's why, again, no charges, right, except for things that are ion charge overall. All right, here's carbonate, and again, that's very similar to the other ones we did, so just kind of scroll it across on your screen there. All right. So let's talk a little bit about some other aspects of bonding. Resonance structures, we'll talk about here in just a sec. But bond length, you don't have to memorize these numbers or anything like that. But when we look at a carbon-carbon single bond, it's 154 picometers distance between the two atoms, 133 for a double bond, and triple bonds 120. When we look at the carbon-nitrogen single bond, 143, double bond 138, and triple bond 116. So what we see in general is as we bring those electrons in to make more bonds, everybody gets closer. So a single bond is longer. When we make a double bond, bring the electrons in, the two atoms get closer. Triple bond, they get closer. And again, we're bringing more of that negative charge between the two atoms, which is going to bring the nucleus kind of closer together on both sides. So the size and distance between the atoms gets smaller as you continue to make bonds, because greater electrons in the middle, negative charge, dragging everybody in as you continue to make those bonds. The sort of relationship for that is, in terms of bond strength, a triple bond is stronger than a double bond, and a double bond is typically stronger than a single bond. They're not like a triple bond is 3 times as strong as a single bond or anything like that, but that is the general trend. So I think about it like a brand new pencil, right? If you have a brand new pencil right out of the box, it's nice and long. You could take it, you could snap it as much as you want. It's going to break pretty easily. You take a couple of chemistry exams, you got like an eraser and a nubbin left right there in terms of it. Super hard to try to break that, right? Because everything's really compact, everything's close together. It's much stronger of a hold together and harder to break. So that's the same way sort of bonds work. The longer the bond, the easier it is to sort of break it. The shorter the bond, a lot harder there is, because all the electrons and that positive negative attractions all together holding it really tight to one another. Any questions on that there? By the way, when we make bonds, right, that is a exothermic process. You have to actually release energy to do so. And when we break bonds, it's an endothermic process. You have to put energy in to do so. So we kind of touched upon resonance structures as we were drawing our Lewis structures, but again, resonance structures really sort of arise when we do have multiple places where we could perhaps make a double bond, and it could give us sort of an equivalent sort of structure. Resonance structures are usually separated by this arrow that kind of heads in both directions. And the real reason we draw resonance structures is one structure doesn't sort of adequately describe sort of what's happening in terms of the bonding. So we can draw multiple structures. They are all sort of equivalent to each other, like we saw there with, I think we did nitrate and also SO2 as well. So here's some examples. Ozone, this is the resonance structures for ozone. Yeah. So again, you only need to do it if you're asked to draw all the possible resonance structures. So if not, it just asks you to draw like a resonance, a Lewis structure. You could draw one of those structures to be sufficient. But definitely, if it mentions, draw them all, you should draw all of them that are possible. This is ozone. So if we go through our sort of journey of drawing it, we will end up with these two structures where we could double bond over here, and we could also double bond over here. In terms of the charges, don't worry about the charges for our purposes here. But again, they're equivalent sort of structures that you can see. This is our carbonate example. And again, that's where the -2 comes in play, actually where those charges are. But we could double bond up on top. We could double bond to the left. And we could also double bond to the right. So once again, those electrons are really sort of, at any given point could kind of be at any of those spots to kind of make that double bond. So one structure maybe doesn't adequately explain the actual bonding that's sort of happening. Benzene ring, we won't come across too much, but it's an organic molecule. And it's a 6-carbon molecule that has 3 double bonds. Each of these points are carbons. And you could draw a resonance structure where the double bonds are on the opposite side. And a lot of times in non-real organic chemistry, you'll sometimes draw it like that, where it is a circle in the middle, and that indicates that those double bond electrons are basically can move around the ring to any of those carbons, and it does still have 3 double bonds. All right, so we got the idea there. So we'll skip through this guy. Just another example of obviously resonance structures and where you can put the different double bonds. So let's talk a little bit about exceptions to the octet rule. Now, there are 3 exceptions to the octet rule, although in this particular class, everything will follow the octet rule. So anything that you draw in this class should follow the octet rule. But I do want to make you aware of some exceptions that you'll come across. And if you continue on to 1A, you'll see a lot of exceptions. But in here, we will stick pretty much to the octet rule and everything should follow it. One exception is an incomplete octet. So there are certain things that are perfectly happy with less than 8 electrons. Probably the most common one that you'll come across is boron. Boron is very commonly electron deficient. It is perfectly happy with 6. Beryllium as well, aluminum. But usually beryllium, aluminum, a lot of times they're more of an ionic type of situation. So boron is typically the one that you will see that will go kind of less than 8. And again, in here, we probably won't see too much of it, but it definitely can go less than 8. So typically beryllium, boron, and aluminum kind of over and down are typically those guys on the periodic table that can kind of do less than 8, and they're okay with that. Another exception to the octet rule is an odd number of electrons, and an odd number of electrons means, frankly, you have 1 unpaired electron. And so you'll have a single dot when you draw the Lewis structure. And in that situation, sometimes they're referred to as free radicals as well. Because they have 1 unpaired electron, they're very reactive. They kind of want to fix that situation. So chlorine is very commonly up in the atmosphere, does a lot of those things where it ends up with kind of like 1 unpaired electron, makes it really reactive to try to fix that situation. So something like NO or NO2 there can end up with, obviously, as you can see here, 1 unpaired electron sort of happening. Now, probably in your chemistry career, the exception to the octet rule that you'll see the most is the expanded octet. And there are certain things that can go above 8 electrons, upwards of like 12 electrons around it. And that is what is known as the expanded octet. That usually happens on the periodic table, or that has the ability to do so. If you find sulfur, go to the right, go to the left, and go down where the nonmetals are on sulfur. Those guys have the ability basically to go above 8. And that is because sulfur is on period number 3, yeah? Which means N is equal to 3. On the 3rd energy level, what orbitals are present? There are S's, P's, and that is the 1st energy level that we see d orbitals appear. And because they have the d orbitals available to them, even though they may not be using it, they have a place basically to stash all the extra electrons in those d orbitals. So anything that's sulfur, like I said on the periodic table, to the right, to the left, and down, which are nonmetals, have the ability to go over 8 and can go upwards of 12. That also means, though, if you look at the periodic table and the period before that, where nitrogen, oxygen, fluorine, all those guys, that is the 2nd energy level, which only has s orbitals and p orbitals. They do not have d orbitals, which means those guys can never go over 8. So they can never go over 8 because they don't have a place to put those electrons. So it's only the sulfur kind of in to the right and down that has the ability to do that. So something like SF6 is an example. Basically, you end up with, and I won't draw all the dots on the fluorines, but they do have obviously their dots as well. Ends up with 2, 4, 6, 8, 10, and 12 electrons around it. Also, why when you Google answers, you shouldn't take the Googled answer sometimes, right? Is if you Google sulfate, you'll get something like this, perhaps. And you put that down for sulfate, and your teacher clearly knows you Googled it because you're not supposed to go over 8. Yes, you're supposed to end up with a structure that looks like this. So just a reminder later, don't Google them. Yeah, draw them yourself. Yeah. So when you draw sulfate, you should look like this with all single bonded and not the double bonded. There's a reason why you see that double bonded thing happen that we don't talk about in this class, which is known as formal charge. This is actually the better structure the expanded octet. But for us, you should obey the octet rule, and you should hit the one that's above there on the left there when you follow our instructions. Any questions on that there? Okay. So once again, you do need to know the 3 exceptions to the octet rule, but you will obey the octet rule when you're drawing your structures in this class. And then when you go to 1A, you could just forget about it and go expanded octet everywhere, which is what happens. What we're going to talk now is about geometry of these molecules. And geometry is basically the arrangement of the electrons around the central atom and also the overall shape of the molecule. And frankly, there's 2 types of geometries we're going to talk about: electron pair geometry. And that describes how the electrons are arranged around the central atom. And we're going to also talk about molecular geometry, which is sometimes referred to as the shape. And that's how the overall molecule sort of structure is, or geometry. I'm going to abbreviate this as molecular geometry from this point on, and EG for electron pair geometry. When we do geometry, the most important place that you should always look is always the central atom. So that is always the thing that you should look at when you're doing geometry. No other atom is important other than what is happening with the central atom. All right, so let's talk about how we can kind of go through this. So we can sort of predict the geometry based on Lewis structures, and really the 2 things that we look at when we're doing geometry and looking at the central atom is the number of electron pairs and the number of bonds. So those, when you draw your Lewis structure and you go to the central atom, those are the most important thing to look at to help you decide what the geometry is going to be. And by the way, most people cannot visualize sort of these things in 3-dimensional space. So the best way is really just memorization of, okay, it has this many electron pairs, this many bonds, it's this geometry. So as we go through it, we'll kind of count the electron pairs properly and the number of bonds. And we'll talk about the 2 names that go along with that sort of arrangement. So the basis of this approach and why we do get different geometries is we're talking about electrons, right? And electrons are negatively charged, which means they do not really want to be near each other. So really the basis of what happens when things come and make bonds is, because they're negatively charged electrons, they try to escape for each other as best as they can. So as they are moving these electron pairs around, the bonded atoms are moving with them, but they cannot completely escape each other because they're all bonded together, right? So, but they do try to adjust themselves in a position where they could kind of live with the space between all the electrons. And that gives us our different geometries that we see in different molecules. So the idea behind this is what's known as VSEPR. And there's basically what stands for valence shell electron pair repulsion model, hence the abbreviation. There's basically 2 types of molecules that we will see. Ones that have no lone pairs or non-bonding electrons on the central atom. So basically no dots on the central atom. And ones that have lone pairs, which means basically you have dots on the central atom. So basically no dots, and basically you got some dots happening. And when we introduce non-bonding electrons to the fold, it does sort of affect the overall shape of it because of a couple of things. There's no longer an extra bond, and that gives everybody a little bit more room to kind of move around because there's one less atom involved. They're just non-bonding electrons. The major thing that you should think about when you do geometry, and only when you do geometry, is anything that is a double bond or a triple bond basically counts as 1 electron pair and 1 bond. So anything that, again, double bond or triple bond, 1 electron pair, 1 bond, it effectively works as one sort of pair of electrons moving around, even though it's double bonded and triple bonded. All right, so let's take a look at how we do this. By the way, as well, if you draw resonance structures like we talked about, you could apply the geometry to any of the resonance structures, and they usually will come out as the same geometry as because they're resonance structures of each other. All right, so let's take a look at really the simplest one that you could do. The simplest one you could do is a diatomic molecule. And whenever you have a diatomic molecule like H2, there is no central atom, which means the only way to connect 2 points is a straight line. So the geometry of anything that's diatomic will be linear. It doesn't matter if it's 2 of the same, doesn't matter if it's 2 that are different, doesn't matter if it's 2 that have a double bond, doesn't matter if it's 2 that has a triple bond. Any 2, the only geometry that you could have is linear because, again, there's no central atom. They will be connected by a straight line. So those are really the simplest geometry that you could do. We got a single bond or a diatomic molecule happening. It's going to be linear for the geometry. You don't really have to worry about it. It does get a little bit more sort of complicated when we do have 3 or more atoms involved in a molecule. So if we have 3 or more atoms involved in a molecule, that is when you want to look at the central atom and figure out how many electron pairs there are and how many bonds that there are. So let's take a look at that when we do get to 3 or more. So our first example here is beryllium chloride, which is an exception to the octet rule. It has less than 8 around it. So once again, we want to focus in on the central atom. And the number of electron pairs here is 1 and 2 electron pairs. And the number of bonds is also 1 and 2 in this case. So starting with the electron pair geometry, it's based on the number of electron pairs there are. So our electron pair geometry is going to actually be linear. And that is because there's only 2 electron pairs, so they go opposite ends of each other to get away from each other, and they end up in this linear arrangement. Because they are also bonds, and the atoms are bonded to those electrons, the atoms move with it, which means the overall molecular geometry in this case will also be linear, or the shape. It is a bond angle of 180 degrees because, again, as those electrons move, those atoms are bonded to it, and they end up, again, being 180 degrees away from each other. Any questions on that there? The next sort of geometry is one where we have a central atom and 3 things attached, like our boron trifluoride, also a exception in complete octet. Looking at the central atom, which is boron, and the number of electron pairs is going to be 1, 2, and 3. Our number of bonds in this case is also going to be 1, 2, and 3. So something with 3 electron pairs, its electron pair geometry name, which I'm abbreviating as EG, is going to be what is referred to as trigonal planar. Some people call it triangular. Because, again, these are all bonded atoms. As those electrons move, so does the atoms. And the molecular geometry will also be trigonal planar. And they call it triangle because it makes a nice equilateral triangle basically happening there. Yeah. Bond angle is 120 degrees. So 3 electron pairs and 3 bonds will result in this trigonal planar. And what's happening is, because of the extra bond, this guy goes upwards and these guys go downward, but they can't get too close to each other. So again, they ending up in a corners of a triangle in this particular case. Any questions on that there? All right. The next example is a central atom where we got 4 things bonded to it. So if we look at our central atom, which again is always the important thing, the number of electron pairs here is going to be 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. And our number of bonds in this case will also be 1, 2, 3, and 4 bonds happening there. So something with 4 electron pairs has an electron pair geometry known as tetrahedral. And once again, because they are all bonded atoms, as those electrons move, so does the atom. So the overall shape actually remains the same. And the molecular geometry, or the shape of it, is also going to be tetrahedral. So it kind of makes a triangle on the face of it and a pyramidal type shape towards the bottom of it. And it ends up with a bond angle of 109.5. And again, because we added in one more atom to the mix than we had previously, now it's got 4 atoms that kind of want to keep away from each other. So they end up resulting in this overall shape here of tetrahedral, which has 109.5. Any questions on that? Up until this point, both the electron pair geometry and the molecular geometry names that we have looked at, have they been the same name or different? They've been the same. And the reason they've been the same is when we look at the central atom, there's no dots. There's no non-bonding electrons. They're all bonded electrons, which means, as I mentioned, as those bonding electrons move, so does the atom. So the overall geometry and shape of it is actually the same as how the electrons are arranged. This changes when we introduce non-bonding electrons to the fold. When we have non-bonding electrons, there's no longer that atom that moves around with it, and it gives everybody a little bit more space to kind of move a little bit more because it doesn't have that extra atom that's also moving with it. There's also a difference in when different types of electrons come near each other. There's ones that want to be near each other, it's okay, and ones that really do not want to be near each other. So that also lends to what happens. And the name that actually changes is the shape, or the molecular geometry name is the name that actually will change once non-bonding electrons get introduced. The electron pair geometry name will stay the same. So that stays the same, but the molecular geometry will change. So let's take a look at what's happening here. When we get electrons near each other, there's sort of good and bad sort of situation. The best situation in terms of repulsion is where we have bonding electrons near bonding, so lines near lines on your Lewis structure. The next best thing gets a little worse is when we got non-bonding electrons near bonding, so dots near lines, if you will. And the worst situation when electrons get near each other is non-bonding near non-bonding, so like dots near dots. They do not want to be near each other, and they actually can escape a lot better because they don't have the atom bonded to it, so they can kind of move a little bit more. And again, as those electrons move, the bonded atoms will move, and what we will see is a change in the molecular geometry of it. So let's take a look at a few examples of where we have these non-bonding electrons involved. First example is SO2, which we drew earlier, and SO2, to remind you, looks something like this. So once again, if we look at our central atom, the number of electron pairs is how many in this case, which would be our sulfur? It has 1 electron pair, doesn't matter if they're lines or dots, everything counts. 2 electron pairs. Double bond counts as how many? Only 1, yeah? So that's a grand total of 3 electron pairs in this case. So again, double bonds count as only 1. It has, in terms of bonds, 1 bond there and 2 bonds there. So number of bonds. So as I mentioned before, the electron pair geometry doesn't change. So something with 3 electron pairs will have electron pair geometry of trigonal planar. But what happens now is with our non-bonding electrons there, these guys pretty much go this way, these guys go this way and down, and we end up with a molecular geometry which is known as angular. Some people call it bent, some people call it bent angular. And what ends up happening is those oxygens now try to escape coming this way, and we get those non-bonding electrons. So the overall shape of it is more of an angular type of thing. The bond angle here is actually based on the number of electron pairs. The bond angle here will be less than 120 degrees. So we're going to go with angular for this arrangement where you have 3 electron pairs and 2 bonds. And we'll see why in just a second, why we won't use bent, perhaps because we're going to use it for another description. Any questions on that there? The next geometry that involves non-bonding electrons is what we see like in NH3. So let's take a look at that here. And if we draw the Lewis structure here for NH3, this is a central atom that has number of electron pairs. Once again, doesn't matter if they're dots or lines. So 1, 2, 3, 4 electron pairs. The number of bonds here going to be 1, 2, and 3 bonds. So once again, something with 4 electron pairs in terms of electron pair geometry name, that is going to be tetrahedral. But here we have our non-bonding electrons is going to go this way. These guys are going to come down, and these guys got to keep some distance between them. And it ends up with a molecular geometry of what is known as trigonal pyramid. And that's because it kind of makes a triangle and that pyramid shape there on the bottom. The bond angle here is actually less than our tetrahedral of 109.5 degrees is the bond angle here. And that is trigonal pyramid. So just to remind you, we saw earlier trigonal planar, which is 3 electron pairs and 3 bonds. That is different than trigonal pyramid. So on your exam and quiz or whatever it may be, do not just write trigonal and let me choose. I failed chemistry, so I'm going to choose wrong and give you an X. Yes. Do not write trigonal. That's clearly pyramid. I mean, planar. I mean, something like that. Yes. So clearly choose. They are different. Any questions on that? All right. One last geometry here to finish up that you're responsible for. I'm not sure where it went, so we'll do it here. I think it got lost. Water. We'll look at water. And when we draw water, it looks like this. And if we look at the central atom here, the number of electron pairs is going to be 1, 2, 3, and 4 electron pairs. The number of bonds here will be 1 and 2 bonds. So once again, something with 4 electron pairs, the electron pair geometry will still be tetrahedral. And in this case, water actually has all of the bad things happening in terms of interactions. We have bonding electrons near bonding, we have non-bonding near bonding, and we have non-bonding near non-bonding electrons. So what happens is those non-bonding electrons try to spread out as far apart. These guys end up coming down. And what ends up happening is we get a molecular geometry, which is known as bent or V-shaped. So this is a different geometry than the angular one we saw earlier. So that is why we're going to use angular for the previous one, bent or V-shaped for this one. This has a bond angle of less than 109.5 degrees. It's about 104 for water. So it's much significantly less than what we see with angular, which is more like 120, a little less than 120. So we will use that differences here. Question on that. That's the last geometry that you need to know for our class. When you go to 1A, there's a ton of expanded octets and your geometry list gets much, much longer. This is a table from your book just to show you. And again, it has all the geometries, electron pair arrangement. And that's really the best way to learn it is number of electron pairs, number of bonds, and what geometry goes for it. You are responsible for electron pair arrangement, molecular shape, and also bond angle. Yeah, so you do need to know those guys as well. Any questions on that? All right, we'll lay it up there for today. We are